All righty. This is section 2-1. It's on rates of change and limits. So let's first start talking about average versus instantaneous speed, and we'll be given some position function, f of t. Time, we're going to use t as our variable, and then the time interval is h. So the average speed is f of t plus h minus f of t all over h. That should look very familiar to you. That's the difference quotient. And we can also think of it as delta y over delta t. Delta, if you remember, means the change in. So that's the change in y over the change in time. Let's look at this first example. A rock breaks loose from the top of a cliff. What is the average speed during the first 2 seconds of the fall? And they give us this function of y equals 16t squared. And we've got from t equals 0 until t equals 2. And they want us to find the average speed. We're going to use our difference quotient, f of t plus h minus f of t all over h. They want to know for the first 2 seconds of the fall, that's your h. That's that time interval because it's going from t equals 0 until t equals 2. And so that time interval is 2 seconds. And so we're going to plug in f of, technically it's t plus h. So t is 0 to 2. So 0 plus 2 is 2. So f of 2 minus f of 0 all over your h is 2 there. And we're now going to plug these values into, y equals 16t squared is your f of t. And so we plug in a f of 2, which will give you 16 times 2 squared will give you 64. And then minus f of 0, which would be 16 times 0 squared, so minus 0, and then all over 2, which gives you 32. And you, of course, are going to use units and say 32 feet per second. And they ask us what's the speed of the rock in this example at the instant when t equals 2. And so for that, it's the change in y over the change in time. And so you plug in 2 in for t, and you're leaving that at h. And at that instant moment, your h, the time interval is 0, right? Because we want it in an instant. So we would plug in a 0 into h and a 0 into h. And so when you figure this out, you would end up with a 16 times 2 squared minus 16 times 2 squared. Oh, that's 0. And you've got a 0 on the bottom. 0 divided by 0. This means nothing to us at this point. You'll learn later on what we can do with this. We can evaluate it further. But for right now, 0 divided by 0 means nothing. And that's where the idea of limits come in. So what is the definition of a limit? The idea is, how does a function behave as you approach a particular x value? And what that means is, what is the y value that corresponds? So when they ask you for a limit, the answer is the y value as the function is approaching the particular x value. Here's the precise definition. We included the whole thing on there because you don't need to memorize this by any means, but this is the precise epsilon delta definition. You assume that f is defined in a neighborhood of c and let c and l be real numbers. The function f has a limit L as x approaches c if, given any positive number epsilon, there is a positive number delta, such that for all x, that distance between x and c, that's where that absolute value comes in, is less than delta. It means that the absolute distance, that distance between your function and the limit is less than epsilon. And then that gives us that the limit as x approaches c of f of x is L. It is that limit. So we've got a note here that says this limit is what the function approaches. right? It may or may not be the actual value of the function, but this is the limit. The limit is what the function approaches. Keep that in mind. Let's talk about a few properties of limits. The limit of k is like a constant as x approaches c. Well, it's just equal to k. So the limit of a constant is the constant. If you think about it, if y equals 3, that's a horizontal line. So it doesn't matter what x value it is, your y value will always be 3, right? So that's where limit of the constant is the constant. And then if the limit of x as x approaches c, well, we just plug in c into x, and our value is c. All right. If the limit of f of x as x approaches c is L, and the limit of g of x as x approaches c is M, so these guys have two different limits, then the limit of a sum is the sum of the limits. The limit of the difference is the difference of the limits. The limit of a product is the product of the limits. The limit of a quotient, dividing, right, is the quotient of the limits, as long as, we have to have that little caveat there, as long as the denominator is not 0. The limit of a constant times a function is the constant times the limit. And the limit of a power of a function is the power of the limits. So here's how this is going to help us. We're going to use these properties allow us to evaluate limits much easier. So for example 3, they want us to find the limit of this function as x approaches c. And technically what we would have had to do without all those properties is, take the limit of each individual piece, and it's a huge pain in the butt. We don't want to do that. No. Turns out what we can do, as long as we're not getting a 0 over 0, we can just plug c in. We're going to plug c into x, and we would get c to the 4th plus c squared minus 1, and then all over c squared plus 5, and you're done. That's the limit of this function as x approaches c. So those properties are quite helpful. We have a theorem on polynomial and rational functions, where f of x is if it's a polynomial function, well, those guys are continuous and everything. So the limit of f of x as x approaches c is equal to f of c. It means you just have to plug in c into x. If it's a polynomial function, you're guaranteed that you can just plug it in. If f and g are both polynomials, and we're trying to find the limit of the quotient of these two guys, you can just plug c into both of them, divide, as long as g of c is not 0. So those are on your notes. So I'm going to keep going. So let's do an example of, let's find the limit of this function as x approaches 2. And what you can do is just plug 2 into all of the x's. So I've got 2 squared plus 2 times 2 plus 4 all over 2 plus 2. And then we evaluate that. Is that 4 plus 4 plus 4 all over 4, which ends up giving you 3. Easy peasy lemon squeezy. Let's look at finding the limit of this guy as x approaches 0. Let's graph it on our graphing calculator. Yes, hopefully you did the refresher on your graphing calculator. Put it in. I would suggest, since it shouldn't matter on the Zoom if you do Zoom trig or Zoom standard. Anytime I see a trig function in there, I'll do Zoom trig. It comes out looking a little bit nicer. So under your y equals button, you'll just put in tan of x divided by x. And you should end up getting something that looks like this. And so we want to know, what's this limit? What's the limit of this function as x approaches 0? Yes. And so you look and wait along this x line. When is x 0? Right here. And so it's right there. What's the y value? Remember, the limit is the y value when x is approaching that 0. And so since it looks like the y value is 1 right there when x is 0, looks like from both sides there, you've got that it's equal to 1. So the limit is equal to 1. So let's look at some one-sided and two-sided limits. We're going to graph this. We'll do it on our graphing calculator also. You're going to put this function here into your graphing calculator under y equals, do the x cubed minus 1 divided by x minus 2. Parentheses are important unless you're using, there is a function that lets you do the fraction bar. So if you're not using the fraction bar function, then you need to make sure parentheses are there. Graph it on this window. This means this is the x min. So what you'll do is once you put in the y equals this guy, you'll hit window, and -10 is your x min, +10 is your x max. X scale, I would just leave it as 1. And then y min, -100, y max, +100. Y scale, you could leave it at 1. What it'll either do is it kind of makes, what the x scale is, make sure I'm saying the right thing. Yeah, the x scale says how far apart the little tick marks are. So honestly, I would probably change the y scale to 10, but I don't think it'll be an issue if you don't. And then you hit graph and you should get something like this. I have these little tick marks set at 10, so that's why I only got that. Now, what they want to know is what's the limit as x approaches 2? So at x equals 2, here's x equals 2. I've got this branch of my graph and I have this branch of my graph. And so at x equals 2, different things are happening depending on if you're coming from the left or you're coming from the right. So if you're approaching 2, but from the left, you're on this ride, you know, and then as it's getting closer to 2, zoom, it's going to -infinity. If you are approaching x equals 2, but from the right, you're on this graph and you're going, and then zoom up, zooms up. So the y values are going to +infinity as x is approaching 2 from the right. Let's see if I did that notation. Nope, I did not. Okay, so because the limit from the left is not equal to the limit from the right, we say the limit does not exist. You need to be going in the same direction from the left and from the right for the limit to exist. So because these are going in opposite directions, then we say the limit does not exist. Now you can have left and right hand limits, and as I'm looking at the notes, it doesn't look like there's a spot to be writing this, but maybe you put it in the little space underneath example 6, hopefully. So this is what it means. You've got left and right hand limits. Do you remember that x approaches 2 and then there's a little plus sign after the fact? That means from the right. And if we want from the left, then we write the limit as x approaches 2 and then the little negative symbol afterwards. That doesn't mean -2, it means from the left. So these are both approaching 2. X is approaching 2, x is approaching 2, but the plus sign after means from the right and the minus sign after means from the left. So now let's look at this, this function. This is the greatest integer function. Your book uses the notation int x, which for greatest integer. You've seen it in the past as a bracket with an extra little line inside, right? That was greatest integer function, and it's this step function, if you remember from pre-calc in algebra 2. Anyway, so we're going to look at the limit as x approaches 2. And so the first one, do I do from the left? Nope, I'm doing from the right. All right, so the limit as x approaches 2, but from the right, means you're coming this way, right? And if you're coming this way, you'd be boop, and then you jump down here, boop, and then you come down here, boop. So as x is approaching 2, and from the right, you're on this little branch here, and that has a y value of 2. So we say the limit as x approaches 2 from the right of this function is 2. Now let's look at from the left. And if you're coming from the left, you'd be and then jump up, and then jump up, doot, and then jump up, doot. Okay, so I know this is an open dot, but that doesn't matter. As x is approaching 2 and from the left, you're right here, and your y value is 1. So we say the limit as x approaches 2 from the left is equal to 1. And um, notice that the function's actual value at 2 is this closed dot. So if you were to ask you what's f of 2, what's the function's value at 2, you would say 2 because of this closed dot. But the limit coming from the left is different. So we would say the limit does not exist as just x approaches 2, right? Because from the left and from the right, they're different y values. We have a theorem that states that the function f of x has a limit as x approaches c if and only if the right and left-hand limits exist and are equal. So this, when it says the function has a limit, it means the limit exists, right? As long as coming from the left and coming from the right, they exist and they have the same value. So that's why if I were to just ask you, I could ask you, what's the limit as x approaches 2 from the right? What's the limit as x approaches 2 from the left? They've got those values, right? And then if I were to just ask you, what's the limit as x approaches 2? The answer would be does not exist, because left and right hand sides need to match. Those limits need to have the same value. So all right, let's look at this example. I know it's a lot on here, but let's walk you through it. It's a piecewise function that you were given. Yeah, and this is the actual like piecewise function, that this little branch here from 0 to 1 is this function negative x plus 1, and then you've got this constant, and then anyway, so there's the function in writing, but they gave you the graph, so that's nice. So let's look at all of these statements. At x equals 0, what is the limit as x approaches 0 from the right? So here's where x is 0. And if you're approaching from the right, you're on this little branch here. What's the y value? It's 1. So that's a true statement. Notice they don't ask you as x approaches from the left because the function's not defined there. So there's nothing, no graph to the left of it. So we wouldn't ever ask you that. For 1, as x approaches 1 from the left, you're on this branch, and what's the y value? Even though there's an open dot there, your y value is still approaching 0. So even though the function's value is not 0 when x is 1, it's actually 1 because of the closed dot there. But the limit is something different. The limit is what was it approaching? And so the limit as x approaches 1 from the left is 0, because that's your y value. Now from the right, as x is approaching 1, you're on this branch, and that y value is 1. So that's why we say the limit of this function as x approaches 1 from the right is 1. Now, because the left and right hand limits are different at x equals 1, then we say the limit does not exist as just x approaches 1. So f has no limit as x approaches 1 because the right hand and left hand limits at 1 are not equal. So we say that the limit as just x approaches 1 does not exist. Let's look at 2. When x is approaching 2 and from the left, you're on this branch here, your y value is 1. As x is approaching 2 from the right, y value is 1. You're going to right there. And so the limit exists, right? Because the left and right hand limits, they're both heading towards a y value of 1. So the left and right hand side limits match. And so we say that the limit exists. So the limit as x approaches 2 is equal to 1. But then if we actually asked you for the actual function's value at 2, that's that closed dot here. So we have the open dot here, but we have a closed dot up here. So f of 2 is equal to 2. So here's one where the limit exists, and it's actually different from the function's value at that x value. All right, at x equals 3, that's here, right? So from the left, your y value is approaching 2. From the right, as x is approaching 3 from the right, your y value is also 2. and f of 3, there's a closed dot right there, so it's also 2. So here's one where left hand, right hand, they match, limit exists, and it actually matches the function's value there. That's going to come into play in a couple of sections when we talk about continuity. It'll be the difference of, um, you know, at 2, this function's not continuous, but at when x is 3, it is continuous because of don't have to pick up your pencil to draw this part of the graph there. And then at x equals 4, the last one, we can ask as x approaches 4 from the left, and your y value is 1, so that's where it's at. We wouldn't ask you as x approaches 4 from the right because the function doesn't even exist there. And then like we only looked at the integers, but any non-integer values, because of these straight lines connecting them, they will have a limit as x approaches all of the little decimal values in between. One last little theorem that you don't need to stress about right now, but the book introduced it. It's the squeeze or sandwich theorem. That is that if g of x is less than or equal to f of x, and that's less than or equal to h of x. So here we're talking about 3 different functions, and if they're on the graph, like g of x might be here, and f of x would be here, and then h of x would be here, right? Then what we can say, and if we know that the limit of g of x is equal to the limit of h of x, and they're both L, all right, well then these two functions are the same. Well then that one in the middle must be also equal to L. It's kind of like, you're smushing them in and sandwiched being in between. Okay, one last little note about your textbook, this Pearson textbook. Exercise numbers with a gray background indicate problems that the authors have designed to be solved without a calculator. So when you go through and do your homework in this book, you'll notice that some of the numbers have gray little backgrounds behind them and some of them don't. And so if they do have a gray one, those are expected to be done without a calculator at all. And then the ones without the gray, they expect you to use the graphing calculator. All right. Very good. Oh, I'm still recording. All right. Have a good one.